Yeah, thanks everybody for convening this. This is it's been an excellent conference so far. And so I'm here to talk about iron 3+, which has been known as a important parameter in metamorphic rocks for a long time. And more recently, in the last 10 or 20 years, we've started incorporating iron 3+ in end members of certain solution models for our phase equilibrium modeling. And the reason iron 3+ presents kind of a problem is that we typically, one second here, isn't working. We typically use EPMA data to do thermobarometry. So we go to the probe, we put our thin section in, perhaps we're going to analyze this biotite here, and we pull out a list of oxide weight percents. And we use these perhaps in combination with other mineral compositions in order to get a pressure temperature point on our diagram, either through conventional or thermobarometry or phase equilibrium model. But the issue is that we're often really interested in this iron number, but this gives us total iron, and we don't know how much of it is iron 2 or iron 3+. So whilst there are ways to estimate iron 3+ by charge balancing for certain minerals like garnet and pyroxene and oxides that are relatively well behaved, you can't do that for things that aren't as well behaved, like biotite, chlorite, muscovite, and staurolite. And these are really quite common minerals, especially in metasedimentary rocks that I'm interested in. So what do you do when for iron 3+ in these minerals? Well, you can go and measure it, but I'm here to tell you that it's pretty tedious and time consuming, and I applaud anyone who goes and does these measurements. The top three here, these are all in situ techniques, but Zanes, XPS, and EELs, they're either not widely used or they need synchrotron or TEM time, which most of us don't have access to. And the bottom two techniques, whilst they might be a little bit more accessible to most of us, they're bulk analyses, they're not in situ. And they're pretty tedious and time consuming, separating minerals out, dissolving them, etc., etc. So most of us really just want an estimate of how much iron 3+ is there in these minerals. And so the next logical question is, well, where do you get an estimate for iron 3+ in each of these minerals? And the best ever study I think that's been done in metapolitic rocks is that of Charlie Godotti and Darby Dyer in this area of west central Maine. And they looked at in 80 metapelites across this range of grade, the iron 3+ contents of these four minerals. And this is great because it has a range of metamorphic grade, but it's relatively restricted in its pressure range and the bulk composition. So perhaps whether or not these estimates are applicable to other terrains is questionable. And then there's a large body of literature of older studies from the 1960s and the 1970s before probe data, where they did wet chemical analysis. And these come from a range of areas with 5 or 15 rocks in each study, but each study in itself represents a different metamorphic grade, a different pressure, a different bulk composition. And this is before the time of MSG, to tie in with the talk. The Michael Atherton, Graham Chinner, Anna Heitinen, John Moore, Bill Finney, Martin Ockbush, these kind of giants of metamorphic from 50 years ago. And so what I decided to do was, well, maybe the best way to get an answer for what iron 3+ is in these minerals is to collate a database. And so I pulled together all the wet chemical, the Mössbauer, the Zanes analyses for these four minerals in metamorphosed silicate rocks. And then if it was in the literature, I pulled out the whole rock analyses at the same time, just so we can compare them. And so before I show you what we have, I just want to give you a couple of definitions. So I'm going to talk a lot about this parameter in the talk, Fe3+, and that's just the amount of iron 3+ over the total iron in moles. And I might also mention XMG. And so when I mention XMG, I simply mean the magnesium 2+ over the iron 2+, not the total iron. So what's in this database? Well, I have 72 studies from 1956 to 2005. They're classified into 40 regions, and I've shown all of them on this world map here. The red dots are where there are 1 or 2 studies and 1 region. The yellow dots, which is Barrow zones and the Moyne, the Alps and the Rioki belt. These are where there are multiple regions and 4 or 5 studies. And then this big blue dot is New England and Ontario, where there's 20 or 30 studies, really, really well detailed in lots of different regions. And so in this database, there's 551 samples, there's 725 Fe3+ analyses of different individual minerals, so many samples have multiple analyses in, 453 biotites, 184 muscovite, 64 chlorites, and 24 staurolites. So it's dominated by biotite and muscovite. And then on top of this, about half of the samples have an Fe3+ analysis for the whole rock. And so to start off with, we just said, okay, well, let's go and take what's the average Fe3+ in a biotite or a muscovite or a whole rock. And I'm showing you that on this table on the right-hand side here. So the average for a whole rock is 0.23 plus or minus 0.16. What you'll probably take away from this table is that the uncertainties are huge. And that represents possibly some variation in the natural data, perhaps some variation between the different techniques used that I won't get into. But it's a start at least. And so muscovite, even though there's not a lot of total iron in it, over 50% of it is iron 3 plus. Biotite 0.11, chlorite 0.08, and staurolite 0.06. So relatively less in those minerals. But we wanted to take this a little bit further and try and see, is there a way we can classify our samples and look at whether there was any change in XFE3 plus with respect to temperature, pressure, and the XFE3 plus of the whole rock? And what we did to do that was make these kind of qualitative classifications. So for temperature, we looked at the metamorphic zones. So these increase in the colors red along the bottom here from chlorite, biotite through to K feldspar at the top. For pressure, we made classifications based on the Fe2 series from cordierite andalusite up to staurolite kyanite. And then for XFE3 plus, because only, less than half of them had quantitative measurements of whole rock, we made an assumption based on the iron oxide. And so we said that perhaps no iron oxide bearing rocks, so those with other accessory phases like rutile or sulfides, those rocks are less oxidized than ilmenite bearing rocks, which are less oxidized than magnetite and then hematite bearing rocks. And we can look at that in a second. So we just did this analysis based on the whole rock, the muscovite, and the biotite, because these are the ones that we have the most data points for. There's not a lot of chlorite and staurolite data. And there's really no change in the XFE3 plus of muscovite or biotite or whole rock with Fe2 series or with metamorphic zone, but there were some interesting correlations with the type of iron oxide, as you perhaps might expect. So this diagram shows you the XFE3 plus on the left-hand side, all iron 2 at the bottom, all iron 3 at the top. And the colors here are the same as the colors on the diagram I just showed you before, with the points representing the mean, the error bars, the standard deviation, and then the range is the colored bars. So you can see we've got no iron oxide, ilmenite, and magnetite and hematite here in the whole rock, and then the same again for muscovite and biotite. And so we get pretty similar whole rock XFE3 plus values for no iron oxide, ilmenite, and magnetite bearing rocks, but considerably higher in our hematite bearing rocks, as one might expect, at least in these metasedimentary rocks. And then, albeit within uncertainty on each of the points, there's a general broad increase in muscovite XFE3 plus with type of iron oxide, and the same for biotite. So we've got some interesting patterns, is what I'm trying to say here, and out of this big database. But if you remember back to the start of the talk, I was talking about the reason we're interested in this is that we now have the ability to do phase equilibrium modeling with iron 3 plus N members. And so we went into Ferric Domino and did some full system MN-NCKF MASH TOW modeling in the latest Holland and Powell 2011 dataset 6.2 with Dick White's 2014 models. And this is great because they specifically have iron 3 plus N members for biotite, muscovite, chlorite, and staurolite, amongst several other phases. And so as a first pass, we just did we took an average of our 231 database whole rocks with this XFE3 plus. And these are the diagrams that we produced. So on the left-hand side is a pressure temperature diagram based on the average bulk composition. The fields are all marked and labeled, but you can broadly ignore those and just look at the different shades of gray. So the different shades of gray, once again, relate to the type of iron oxide present. So we have magnetite at lower pressures, hematite at higher pressures, a small field with just ilmenite here, no iron oxide in the white field, and then hematite at lower temperatures down here. And then we also decided that we'd make a T-XFE3 plus diagram. So that was made at 5 kilobars along this dashed line, and that's shown on the right-hand side here. And so all iron 2 at the bottom, all iron 3 at the top. And you can see we go from ilmenite to magnetite and through into hematite-bearing rocks, as we might expect, as XFE3 plus of the whole rock increases. And what we're really interested in is, as much as we're interested in the stability fields of these different iron oxides, we want to look at how much iron 3 plus is predicted in the biotite and the muscovite, these minerals that we have a good grasp of. So these diagrams here show you the colors represent the XFE3 plus in biotite and how that varies across where biotite is stable below the solidus. And the black lines are the modal abundances with the white numbers. You can likely ignore those for the minute, and we'll just look at the colors. So roughly, biotite goes from lower values of XFE3 plus 0.04 to 0.16. And that's, with an uncertainty close to what we see in our biotites, right? We get about 10% iron 3 plus. We don't see this pressure or this change with temperature that's predicted by the models, but the numbers quantitatively are pretty close. On the TXFE3 plus diagram, this one on the right, bear in mind these shadings are scaled differently here. The models go from about 0 to 0.5 at 0.9 XFE3 plus in the rock. And so a little bit less than what we see in terms of our change. We go from 0.08 to 0.18. And so the magnitude, the change itself is correct, but the magnitude of the change is perhaps a little bit off. And we see similar things for muscovite. Muscovite has this kind of change across PT here, and it goes from 0.15 to 0.45 XFE3 plus, but that's a little bit lower than what we expect in muscovite. I mean, these numbers are a little bit uncertain, but it's less than what we expect. And then on the right-hand side, we have our TXFE3 plus diagram, and we go from 0 XFE3 plus to 1, and we maybe go from 0.5 to 0.8. So there's always about 50% XFE3 plus in our muscovites. So what does this all mean? Well, just to conclude, look, we've got this database. There's 541 natural samples with lots of minerals and whole rocks with nether XFE3 plus. Here's our averages on the right-hand side. We found some correlations with the type of iron oxide. We see that mean XFE3 plus values of whole rock are similar for ilmenite, magnetite, and no iron oxide, but much higher for hematite, and that perhaps there's a general increase in muscovite and biotite with the type of iron oxide. The thermodynamic predictions, well, they're good for biotite, a little low for muscovite, and the variation in TXFE3 plus of muscovite and biotite is what we see, so that's great, but this variation they predict with pressure and temperature, we don't perhaps see in nature. So for future work, I'm not saying this is the answer. Please go and measure iron 3 plus if you have the means that you can. I think that's ultimately the best way. But if you can't, then at least make an estimate. And so this database will be freely available once it's published for you. I can either use our estimates, you can compare it with data that are similar to yours, and maybe this will help us develop the thermodynamic models, or maybe even pinpoint which minerals we need to make more iron 3 plus measurements in the future. So just some acknowledgements that this wouldn't be possible without the painstaking work of these petrologists from 50 years ago in obtaining wet chemical analyses before EPMA. And also all the universities that have scanned theses and all the journal articles that I was able to take these analyses out of, because it wouldn't be possible. And finally, I have to thank COVID-19, because without the pandemic, the labs wouldn't have shut down and I wouldn't have had time to sit around and collate such a database. So thank you very much. If anyone has any questions, just ask them now, I suppose, or in the chat. And if not, send me an email.
Thanks, Jacob. Yeah, we're running a bit late, but we do have time for some questions, because so Bernardo has a question. Are there data for garnet?
Oh, that I've forgotten. No, there aren't in data, because I think, it's thought that garnet in metapolitic rocks typically has very little iron 3 plus, and most of you can estimate that from EPMA data, I would argue. So there's no need for actually to include that in the database. But if you feel otherwise, Bernardo, or have an idea, let me know.
And he has two questions. Can 20% Fe3 plus in bulk of ilmenite-bearing pearlite be overestimated due to alteration?
Yeah, that's a good question. I mean, we have to think about alteration in both the mineral analyses and the whole rock, and whether or not that's contributing to it. That might well be the case. There appears to be about 20% in most metasedimentary or metapolitic rocks. I don't have the answer yet. Pick a fresh rock when you analyze it, I hope is the answer, I think. Yeah.
Okay. Doesn't seem to be any more questions. So thank you, Jacob.